Hello, everyone, and welcome to this talk. We hear a lot about the effects of climate change in the media, such as changing weather patterns, flooding and droughts, as well as the need to adopt sustainable technologies. But what does that look like in our own homes, and just how important is geology in achieving net zero and adapting to climate change? So in this talk, in the next 45 minutes or so, BGS geologist experts, Alan MacDonald, Emma Deedy, and me, Mike Stevenson, will tell you a bit about why geology is so important to fighting climate change. We're basing this talk around a home, perhaps a home a bit like yours. You can see it there. So listen in for the next 45 minutes or an hour and find out about how electricity supply might change, how we might heat our houses in the future, why water in the rocks under our feet is so important, where we'll get the metals we need for our electric cars, and how we'll get from the couch to net zero. So a lot of energy is used in heating buildings. For most of us, the heat in our houses comes from the hot water in the radiator. But this water is mainly heated by natural gas burned in a boiler. We've all seen the steam spouting from the boilers in houses on cold days. Burning this gas produces carbon dioxide a lot. Something like 19% of the UK's greenhouse gas emissions come from warming up the places where we live and where we work. And more than 3/4 of this comes from our homes. So wouldn't it be great if we could keep our homes warm without emissions? One way that this could be done is by using geothermal. And this is not the kind of geothermal in volcanoes and geysers, but it's just warm water in the rocks under our feet. You might ask, how can just warm water do all this heating? The answer is that there's just so much warm water under the UK, and also in many other countries across the world. So what if we could get to this huge volume of warm water in the rocks and convert it to a smaller, concentrated amount of even warmer water? Well, the answer is already here. We can use boreholes to get to the water, and we can use heat exchangers. And these heat exchangers swap the heat from the underground water to clean water, and they boost its temperature. Then we can pipe this cleaner, much warmer water straight into people's houses. The heat that we would be using would be coming, or it would be in a mix from deep in the earth and from the sun. So it's actually completely renewable. It's also a form of base load power, a very continuous and reliable source. In fact, it's the only truly consistent, not intermittent, renewable energy source. But there's another really great idea too: old coal mines. Because Britain is an old industrial country, around 1/4 of our residential homes, the homes we live in, are above old coal mines in our big cities and their surroundings in the north of England and Scotland. None of these underground mines at the moment now are operating. And so without pumping, they've basically filled up with all this warm water, the same warm water that I was talking about before. And this warm water circulates very freely underground because of all the tunnels and shafts. It means that the warmth is easy to get hold of, and it's even easier than in the simple geothermal that I mentioned earlier. So BGS, British Geological Survey, is very interested in this heat and how we might actually use it, and also how fast the heat comes back when we do use it. So we've actually built an experimental test site, which will allow us to find out about heat and the way it moves underground. This is called the UK Geoenergy Observatory, and it's in Glasgow. We're doing experiments right now, and it looks like there's plenty of water, and it's warm enough, if we concentrate it, for houses and villages in the towns above. So I'll hand over to Alan.
Thanks very much, Mike. It's really great to have access to clean water in our houses, be it for that shower in the morning, washing the dishes, flushing the loo. And then, of course, there's the real essentials, that cup of coffee or tea in the morning. Having clean water on tap all day, every day, is something that we often take for granted in the UK. Many people in different parts of the world are not quite so lucky. But have you ever imagined where our water comes from? What's at the other end of that pipe coming into our houses? Well, in the UK, about 2/3 of our water comes from rivers, lochs and reservoirs. The rest comes from groundwater. That's water stored naturally under the ground. Wherever it comes from, the water is treated to make sure it's safe to drink and then pumped to our houses. And on average, in the UK, each of us uses 142 litres of water every day. I mean, that's a lot of water. Just imagine 140 drinking water bottles. We don't drink it all, of course. Most of it is flushed down the loo or goes down the plug hole in the shower. Now, climate change is making our weather much more variable. Scientists are predicting that with the atmosphere heating up, rainfall will become less predictable, with periods of very heavy rainfall and longer periods of drought. That provides a real headache for the engineers supplying our water. And one of the solutions is having more storage available, so that in times of heavy rainfall, we can store the water for when we need it during drought. This can mean building more reservoirs or transferring water across the country from drier areas to wetter areas, or from wetter areas to drier areas. However, there is a natural solution that's often available. Groundwater is an excellent natural solution for water storage. Aquifers are nature's reservoirs. There is much more water stored in the cracks and pore spaces in the rocks beneath our feet than there is in our rivers, lakes and lochs. Across the world, it's 30 times more. So where does groundwater come from? Well, it's part of the water cycle that we all learned about in school. When it rains, excess water that's not used up by the crops or the grass either runs off to our rivers or slowly infiltrates into the ground, where it can accumulate in small, tiny pore spaces within granular rocks like sandstones or cracks in hard rocks like granite. And then it flows slowly over years, decades, centuries, or even thousands of years to discharge in springs or as base flow to rivers. This natural store of water, it's not just dependent on last summer or last winter's rainfall, so it's a great buffer to changing weather. Now, one of our jobs here at the British Geological Survey is to map out the different rock types under our feet to work out which ones are good aquifers and store a lot of water and which ones aren't so good. We also develop and use lots of different methods to work out how old the groundwater is, and also the chemistry and quality of the water to make sure that it can be used sustainably and make us much more resilient to climate change. So in the future, many more people in the UK and across the world are likely to be using groundwater to make that morning cuppa. Now, I'm going to pass over to Emer, who's going to tell us some more things.
Thanks very much. So transportation is an essential part of our everyday lives. We use cars, taxis, trains and buses on a daily basis. Did you know that transport is currently the largest greenhouse gas emitting sector in the UK economy? And in 2019, it was responsible for 27% of the total UK greenhouse gas emissions, with over half of these emissions produced by internal combustion engine cars, those that are powered by petrol and diesel. To try and address this issue and meet the commitment of net zero carbon emissions by 2050, the UK government plans to ban the sales of new diesel and petrol cars and vans from 2030. That's only 9 years from now. An alternative car type are electric cars. These run either totally or partially on electricity and are powered by lithium-ion batteries. So similar to the battery in your phone, they'll be charged up, used for travel, the battery will run down, and then they'll need to be recharged. Benefits of these cars, they have lower CO2 emissions, improved local air quality, they don't directly use fossil fuels, and there's potentially lower maintenance because there's fewer moving parts and also could have potentially have lower running costs. However, of course, with any of these benefits, there's some challenges that also need to be addressed. Electric vehicles get propulsion from an electric motor instead of the internal combustion engine. The power to drive the electric motor comes from a large battery pack. But did you know that electric vehicles contain about 3 times more metal than regular vehicles? While they do produce lower emissions, they do require more in terms of resources. There are lots of different metals in electric vehicles. In the battery, this includes lithium, cobalt, nickel, and manganese, for example, while the rare earth elements are essential to make the large magnets that are in the motors and also in the smaller magnets that are across the vehicle. So we know that electric vehicles have the power to reduce their carbon footprint, but there are things we need to consider. So this increased variety and amount of metals in each vehicle. And if we do convert to using more electric vehicles, we'll also need to increase the number of charging points across the UK. So those will be the ones at your houses or at your place of work, maybe even on the street. But it'll also require a network of charging points right across the country. And building this infrastructure is going to require a lot of raw materials and especially will require a lot of copper. And the carbon footprint of extracting those metals and raw materials will also need to be considered. So where do these metals come from? There's a saying that if you can't grow it, you have to mine it. And realistically, that is the case. Metals occur in deposits, typically in the ground, in minerals that are extracted and processed into metals that are then used to manufacture goods. And one of the jobs we do at BGS is work on different ore deposit types to understand how these deposits form, where they occur, and what minerals and metals are hosted in. Mining is only the first step in what we call the supply chain for metals. Metals such as cobalt come from a few mines in the Democratic Republic of Congo and a couple of other mines across the globe, while lithium production is mostly dominated by countries in South America. Rare earth elements come from China mostly, and things like nickel, graphite, and manganese are produced much more widely across the globe. Another aspect of the work we do at BGS is to look at supply chains for lots of different commodities to understand what is happening globally. So in developing the electric vehicle industry, we need to consider the carbon footprint of the metals that are used to make the cars, and of course the source of energy that we use to charge our vehicles. However, the reduction in the emissions from combustion engines, the use of recycled materials, the development of more efficient batteries, and of course using renewable energy as a source of charging our vehicles will make a difference. Okay, over to you, Mike.
Hi, it's me again. So household stuff. Our homes use a huge amount of steel, cement and plastics and other materials that have to be strong and durable. And we'll continue to need these manufactured materials. And as the world's population grows, people in emerging economies will want these household goods too, as well as fertilizers, lubricants, and a range of chemicals. So huge industrial installations around the world supply these materials, converting raw materials into finished products. Factories like steelworks, cement factories, fertilizer factories, and refineries tend to be in groups called clusters because they need the same resources and types of land and access to the sea. But as you can imagine, these clusters have really big emissions. Europe's industrial clusters represent about 20% of Europe's greenhouse gas emissions. And in Britain, the map of clusters looks like this. You can see it there. And you can see the size of their emissions. You can see Humberside, for example, and Teesside and Grangemouth. So there's a really big job to decarbonize these clusters, to decarbonize the manufacturing of the goods that we all use. But actually, this decarbonization of clusters is already happening. Big steelworks and refineries can be decarbonized by capturing the carbon dioxide associated with the energy that they use and some of their ingredients, and then injecting that carbon dioxide deep into the rocks under the North Sea. And this is called carbon dioxide capture and storage. It was on the news tonight, actually, if you saw that. This is already happening in a few places. We can also use hydrogen to power the clusters. Hydrogen is a gas that produces only water vapor when it burns. And hydrogen can be manufactured from natural gas, for example. But this also produces CO2. So again, carbon dioxide capture and storage can be used to reduce the emissions associated with making hydrogen or hydrogen manufacture. Or even better, hydrogen can be manufactured by electrolysis using renewable electricity, though it's expensive at the moment. The hydrogen could be used as a fuel in the clusters, but also as a kind of battery for kind of storing extra renewables electricity when the sun's really shining a lot or the wind's blowing a lot. So geology is really important for this cluster decarbonisation, because geologists like me and Alan and Ema will find the places to inject the carbon dioxide, to remove it from the atmosphere, but also because we'll have to find places underground to store large amounts of hydrogen. We'll not be able to have or sustain a big hydrogen economy without a lot of storage space underground for hydrogen. So rock salt is probably the best place for this. And the BGS, the British Geological Survey, is right at this moment busy mapping areas of rock salt in preparation for these clusters setting up hydrogen systems. So again, I'll hand over to Alan.
Thanks, Mike. I get to talk about one of my favourite subjects now, which is food. So nowadays our food comes from all over the world, and we love the diversity of food that we can eat, be it sort of bananas from the Caribbean, our tomatoes and cucumbers from Spain, grapes from India, nuts from California, Scottish lamb, English apples, and of course, sugar, maybe from India or Brazil. That keeps us all in our favourite drink, iron brew. But in a low carbon economy, we need to think really carefully about the energy we use to transport and produce our food. And we're all learning about the carbon cost of some of our meat production, the infamous belching cows, or the air miles for fruit and veg, cutting down virgin rainforests for soya or oil plantations. This has led many people to cut down on meat and dairy products. You know, for example, Prince Charles recently told us he's meat and fish free for several days a week. It's not always a simple equation though, and global trade has also meant that some crops are grown in places in the world using less energy because it's warmer with the sunshine. What we often forget about is the water needed to produce crops. Some 70% of the fresh water withdrawn all over the world is for irrigation. And often it's groundwater that is relied on to irrigate crops. And this high level of pumping can have some serious impacts, particularly in areas where water is already scarce. In some countries where they're growing food for us, water levels in aquifers are reducing dramatically. For example, in California, groundwater levels have reduced so much in the past 100 years that the ground level has actually fallen by 7 meters as the aquifer has become compressed. In northern India, rice and sugar production has led to rapidly falling groundwater levels, which is drying up shallow wells used by some for drinking water. And even in the UK, our intensive agriculture has been polluting our water supplies with nitrate and pesticides, meaning that the originally pristine groundwater needs to be treated before we drink it. Now, farmers have done a great job in doing what we wanted them to do, producing the food we want safely, humanely, and at a great price. Now as a society, we're beginning to think about how they can also be rewarded for looking after the environment. BGS has been working with partners in the UK and across the world to map out groundwater resources, how quickly they're being replenished, the quality of the water, and where the resources are being depleted. I've shown a map there of some work that we've done across Africa. Groundwater depends critically on the geology, and by understanding how these aquifers work, we can help manage them in a way that allows food to be grown without harming the environment. This may involve switching between groundwater and river water throughout the year, channeling excess floodwater into aquifers to be used at a later date, and being more efficient with our use of water. When in the UK, we now control the amount and the time of year that nitrogen and animal waste and slurry is applied to the land. And that's really helped limit the pollutants that get washed into rivers and into our aquifers. And in a rare good news story for climate change, we've found that in parts of the world, climate change may actually increase the amount of groundwater available. In a series of experiments we've done over the last 10 years across semi-arid areas of Africa, we found that the more intense storms that seem to come with climate change seem to make it easier for rainfall to get down into the aquifers and raise the water table. So what will our future low carbon society look like with regards to food? I mean, there are exciting new developments in growing food in a way that uses less water and nutrients and carbon, recycling the nutrients and the water. These are kind of futuristic vertical farms are being trialled here in the UK. And maybe they might enable lettuces at some time soon to be grown in our supermarket car parks. There are other solutions too, like using solar energy for pumping water. More than 6% of all India's carbon emissions come from pumping groundwater for irrigation. So changing this to solar would make a big difference. And hopefully soon, all our food will be labelled with the carbon and water used to produce it and the impact on the environment from growing it. That can help us make decisions about what food we buy and give us plenty more reasons to enjoy eating locally produced food. Over to you, Emma.
So we've already talked about electric vehicles, but what if you don't use a car? Maybe you live in the city, or you're trying to reduce your own carbon footprint by using your car less. Walk, cycle, maybe even on an electric bike. And we also use public transport where it's available. In recent years, you might have seen new electric buses in towns and cities, and these also operate using a lithium-ion battery, and so have similar challenges to the production as similar challenges as we've seen in the production of electric vehicles. So Mike has described how hydrogen can be produced either from hydrocarbons or even better using renewable energy to produce hydrogen from electrolysis. This hydrogen can be used to power public transport in hydrogen fuel buses. These buses are powered by an electric powertrain where fuel cells convert the chemical energy of hydrogen into electrical energy. The hydrogen itself is stored in pressurized tanks, typically on the roof of the bus, and the buses produce no tailpipe emissions, with the only waste product being water, and so their class is zero emission capable. Refueling of these buses is similar to filling up for petrol, with hydrogen stores at bus stations filling up buses every day. Similar technologies are also being applied to bigger vehicles, such as heavy goods vehicles. Although this technology is only really being developed at the moment. There have also been plans to use hydrogen to fuel our bin lorries. Glasgow City Council has approved the purchase of 19 hydrogen fuel bin lorries. These have the advantage of having no associated air pollution, they're quieter, and they'll only produce water as a waste product. We must remember that we need to consider the source of the energy used when we are creating the hydrogen for these new technologies to make sure we're not actually causing any extra emissions. To use hydrogen as an alternative fuel to fossil fuels to transport people, goods, and rubbish, we'll need to develop new infrastructure networks, and these will require raw materials. And we need to consider the carbon footprint associated with extracting these. Over to you, Mike.
Thanks, Seema. So the next thing is we need to decarbonize electricity. We need to decarbonize power. It's likely that electricity will be the most important basic energy provider in the UK in the world as it decarbonized. We'll have electric cars and buses. We'll have industries, or more industries run by electricity rather than fossil fuel. We'll need an enormous amount of electricity in the world for these reasons, and also because demand for electricity is going up as the population increases. Much of this new electricity will be needed in the developing world, in the emerging economies. So all this new electricity will have to be generated without significant emissions to the atmosphere. Luckily, electricity is already being rapidly decarbonized in many countries, mainly through wind and solar or hydroelectricity, as you can see here. In Britain, we'll probably continue to use more wind and solar, which are intermittent providers of electricity. So we might use batteries to fill in when the wind is weak, when the sun isn't shining, or we might use compressed air energy storage. And this is a really new, clever idea, which can store enormous amounts of energy for later use. It's a bit like a huge battery. It's where air is compressed in a deep cavern using energy when it's plentiful, when using electricity when it's plentiful, ready to be released to drive a turbine when the energy is needed again. And in emerging economies, energy demand will rise because of fast growing populations and increasing living standards. Many emerging economies are likely to continue to use coal to generate electricity. We can already see this happening. And they'll probably use coal to generate electricity for many years to come. Maybe that the only way that this electricity generation can be decarbonized is with carbon dioxide capture and storage on coal or even on gas power stations. This will need a lot of geological input because power stations will have to be linked up to carbon dioxide pipelines that serve other power stations and factories, and ultimately to the offshore or perhaps onshore geological formations like sandstones, where this carbon dioxide can be disposed of. So I'll hand over to Alan.
Thanks, Mike. I'm going to talk now about floods. So climate change is also forecast to lead to more risks of flooding in the UK and many places around the world. In the UK, between summer of 2019 and spring 2020, we saw a succession of devastating floods in the UK, Wales, northern and central England, southern Scotland. This included Storm Dennis. Rivers burst their banks, flooding thousands of houses, closing schools, damaging roads, cutting power. Several rivers saw their highest ever recorded flows. So climate forecasters say that this is likely to get worse in the future as a warmer atmosphere means it can pick up and hold more moisture and lead to heavier rainfall events. Now, concrete walls are generally great at holding back floods, and our engineers have been protecting our towns and cities for many years against the worst effects of flooding. But we can't keep building walls higher and higher forever. It's not only expensive, it also destroys what's part of what we like about living in the UK, being able to walk along a riverbank or get into the water or canoe, swim, paddleboard. So with an eye on the future, people are beginning to think about more natural ways of managing our catchments and rivers that can help to reduce flooding and building with nature rather than against it. First of all, there are the obvious things like making more room for rivers in our society, recognizing that sometimes they do need more space to flood. But there's also the possibility of getting the land to soak up more water and to slow down the flow in river channels. And this is kind of where geology comes in, because different rocks and soils soak up heavy rainfall at different rates. Some catchments are really good at stopping flooding, but others seem to respond in a much more flashy fashion. And a lot of that is due to the geology. Where the ground has low permeability, the rain doesn't infiltrate so well, and the water can run off quickly into nearby ditches and rivers, causing rapid flooding. But where the ground is permeable, heavy rainfall can soak into the ground and then it's released much more slowly back to the rivers. Often the makeup of the soil actually reflects the underlying geology. So if a catchment is on sandstone, the soils can be sandy and then good at soaking up water. But if the geology is made of mudstone, the soils can be very clay-rich and the water just runs off. Another thing that can affect how permeable a catchment is was the presence of glaciers thousands of years ago. Most of the UK north of London was covered by glaciers at some point, and they often left behind deposits of sand or clay. And we've been doing a number of experiments at BGS looking at how these deposits affect flooding. And we've been finding that the presence of these old icy deposits can be really important. So we can't do much to change the geology. Don't think even the powers of Boris Johnson or Nicola Sturgeon can command another ice age, but we can change how we use the land. For example, growing trees can change the soil structure and how it soaks up the water. Different trees change the soil in different ways. We found that old, established, native deciduous trees are some of the best at soaking up water. Other things that affect the soil are the density of grazing animals or how we plant our crops. And we should definitely try to cover less of the ground with tarmac or concrete. Some of the natural measures that are showing most promise in reducing flooding are slowing the flow of rivers by building little leaky dams, trying to replicate the natural process of trees falling over a river. These allow water and watery animals to move up and down the river, but they slow up the flow of the river when the river level rises. Another promising method is to dig ponds in the headwaters of catchments that can fill up rapidly during a storm. Here in Scotland, BGS have been helping run a long-term experiment in the Eddleston catchment on the River Tweed, where we've been testing how effective some of these different measures are. Building with nature can have lots of other benefits too, for wildlife and our own mental health and enjoyment of the countryside. Of course, we'll still need concrete. We can't throw away our amazing engineered flood defences. But hopefully by building with nature, we can reduce some of the risk of flooding. And knowing the geology, the soils, and how our glacial history is still impacting our landscape today is fundamental to designing these things well. So in a future low carbon world, our wonderful countryside will be managed in a way that helps soak up carbon and water and should hold on tight to the carbon while releasing that water more gently back to our rivers. Now back to Emer.
Thanks. Overall, as we see increased development of metal and other raw material intensive technologies such as electric vehicles, hydrogen fuel cells, solar panels, wind turbines, and we're also seeing increased construction, which uses concrete and steel, making hydroelectric dams or flood defences. It's important to recognise that we'll need additional raw materials to make these things. The World Bank has predicted that we'll need more than double the amount of raw materials by 2060. In order to address this, we will need to extract more. However, the way we do that is really important. So ensuring lower environmental impact of extraction, assessing the impact on the groundwater, ensuring clean and safe extraction, processing the metals using renewable energy. And of course, there's also the other source of materials, and that is recycled material. So you'll all be aware of the importance of recycling. Putting your clean, dry recyclables in your recycling bin, particularly important for plastics, as these are made from hydrocarbons and have a significant carbon footprint. You might also collect your used AA batteries, small electronic appliances like your old kettles, and maybe blown fluorescent light bulbs to bring to your local recycling centre. What are recycling metals? There are very few metals that we are very good at recycling. In the home, we recycle our tin foil and our cans, and these are made from aluminium, which is a real success story for recycling. Industry is very good at recycling gold and platinum and other precious metals because they have such high value. But what about all the other metals? There's a lot of research ongoing at the moment on how to recover metals from electric car batteries and from permanent magnets that are in the motors of electric vehicles and wind turbines, for example. We also need to consider how we can use recycled metals in our products. So many phone companies now are manufacturing mobile phones using greater and greater amounts of recycled metals, and that's a really good thing. However, when you consider that even if we recycled all the objects we can now, as demand is increasing, we simply don't have enough metal available from recycling to manufacture everything new. So we have to extract new raw materials to meet the demand. But there are things we can do to increase the amount of metal recovered from recycling. We currently use alloys or mixtures of metals to make our products that don't occur in nature. And we don't quite have the technology to separate them. So developing that technology is one way to do that. Our products aren't really designed in such a way that recycling is easy. So we need to design in the fact that we're going to recycle these when they come to their end of life. Hopefully this is being recognized, and there are definitely changes in the industry, recognizing that recycling is part of the solution, and moving towards that more circular economy is a real step forward. Thanks, Mike. Over to you.
Thanks, Emma. So we've come to the end of the talk. So Alan, Emma and me have shown you about how our electricity supply might change, how we might heat our houses in the future, why water in the rocks under our feet is so important, and where we'll get the metals that we need for our electric cars. For geologists, this is a really exciting time, helping to solve one of the biggest of the world's problems. Some of these geological technologies, like geothermal and carbon dioxide capture and storage, will make a difference, and our geological knowledge will help to make batteries and to supply water where it's needed for people to live and to grow crops for food. But of course, all these will have to take place alongside other commitments from people to insulate their home better, try to reduce their own carbon footprint, perhaps by taking fewer car journeys, eating food with a smaller carbon footprint, and recycling as well. Perhaps to take the train and bus more often to work, for example. So we've done all the talking up to now. It'd be great to have your questions. We've got, I think, 18 questions in the Q&A. So please keep putting questions in the Q&A. Over to you now. We'll start answering those questions.
Hi, everyone. So as Mike has said, we've got some really interesting questions. So we'll get started. Actually, first one for yourself, Mike. And the attendee has asked, if we dig deep enough, is geothermal available everywhere?
That's a great question. In fact, this warm water tends to be anywhere where there are rocks of a certain type. Actually, the rocks that Alan was describing, these aquifers. So wherever there are aquifers, there tends to be warm water at a certain depth, firstly because of the natural warmth of the earth, but also because some of the solar heating of the earth actually transfers its way down into the subsurface. So anywhere where there's aquifers, there tends to be warm water if it's deep enough. I mean, this is very separate from the kind of Icelandic, New Zealand sort of, geysers and boiling lava and that kind of thing. It's just very tepid sort of warm water, but the point is there's so much of it. And if you've got millions of cubic kilometers of rock which contains warm water, then actually being able to concentrate that, for a comparatively small number of, houses, for example, is something that's quite possible. So I would say there's geothermal possibilities in most countries.
Great, thanks, Mike. So this next question is for Emma. And the question asks, do you think it's possible that we can secure enough metals we need for the volume of electric vehicles required in the UK?
Great question. At the moment, the UK does not produce any of its own raw materials, those metals I particularly mentioned. So lithium, graphite, manganese, cobalt. The UK doesn't mine any of those. And even if they did have those mines, the ores, which is what you're extracting from the ground, would still need to be sent to other countries where they would be processed. And at the moment, For most of those things, they're processed in China. So we would still need to ship our ore out even if we had it. So actually what we do now is we import most of our goods. We're quite dependent on imports. And so the mining or the metals industry has an excellent setup for that already. There are trade agreements, there are MOUs with different companies. Certain companies would have an agreement maybe with their parent country where they might be able to import metals directly from them. So I think that supply is already quite secure. As we increase the number of EVs, if all these factories do come on board and all these, we will obviously have to increase the amount of metal we import, but that will be the case all over the globe, and the production of those metals will have to happen to meet that demand.
Great, thanks, Emer. I think Alan thought he was getting off the hook here, but we've got a question for Alan. Should new buildings, and certainly new construction or plans for new construction of any type, have their own inbuilt water storage by law or by regulation?
Gosh, that's a cracker of a question. I'm going to dodge it in terms of the legal answer, whether people should be forced to do it or not. But I think we've all been maybe increasing a little bit the water storage in our houses recently. If you think of most of us in the garden will have water butts for watering our garden. So we've kind of been changing a little bit of our behaviour ourselves and how we store water. I mean, I think we're very fortunate in the UK that we do have really good water authorities, if you're in Scotland, or water companies in England that do a lot of that storage for us. And I think there has been a good change, I think, in the way that we behave, that we don't waste water very much. Well, 142 litres per day, that UK average, compared to the US is a lot lower. And I think as consumers, if that's the right word, or users of water, I think we're generally quite good at not wasting it. So by law, I'm not sure about that, but I think by behaviour, we are storing some water for various uses.
Thanks very much, Alan. So the next question is back to geothermal and for Mike. So the question asks, if we have all of this warm water in mines, how many homes in the UK could they heat? Do we have any figures for that?
Yeah, and we don't really. No, I mentioned this UK Geoenergy Observatory that we've built in Glasgow. And that's really the purpose of research. That's what we're here to do, to try and work out what the possibilities are of this mine water geothermal. It's kind of a new idea, really, kind of surfaced in the last few years. And our test site, our experimental test site that we have, will do precisely that. It's what we're going to try and do is measure how much heat there is, first of all. So we've got an idea, but we'd like to be a bit more specific, and a bit more precise. But what we're also interested in is if you take the heat out, which obviously we want to do, like heat exchange it, obviously we're going to cool down the water that we're using. How fast does it warm up again? Because if it warms up really slowly, then we're kind of mining the heat, which is not really very good if we're using it faster than it's replenished. So these are the sorts of questions that we're trying to answer. I mean, that's what science is about. So I don't think we can answer what the potential is yet, but we think it's good.
Thanks, Mike. So we've got another question for Alan, and that is, will any of the water resources research be turned into teaching resources? I can see plenty of use for it in my classroom.
All right, that's great. Glad you're finding it useful. I mean, I don't have current plans to put it into teaching resources. I do write quite a bit for universities, so chapters and textbooks and stuff for university students and things like that. But if you think there's things that could be useful for schools, yeah, drop us an email and we can see what we could provide that might be quite useful. I think you're right. I mean, groundwater is often a little bit difficult to teach, and it's a little bit forgotten about. It's out of sight, out of mind, but it's a third of the world's water supply is from groundwater, and it's going to be more and more as climate change makes surface water more variable. So I think we do need to think more about how we find imaginative ways to make groundwater more visible. And next year, 2022, is the World Water Day is going to be all about groundwater. So we're hoping there's going to be a lot more resources available next year, because a lot of people are really concentrating on making groundwater more visible to everybody.
Thanks, Alan. I could just add a little bit to that as well. So we've got a really active public engagement team at BGS. And I think they'd love to hear of ideas or demand for certain teaching resources. I can't say that we'll be able to provide them or what time frame, but hopefully in the communications side about this event, there will be a BGS corporate communications email address. If you have any needs or requests like that, if you could just email the inbox and we'll get back to you and let you know what is available. Okay, so on to the next question, and this one's for Emma. There are claims that electric car batteries have a limited life and can't be recycled, and that wind turbine blades have issues preventing recycling. Is any of this true?
That is a great question. One of my favorite topics. I love recycling. So it is true that electric car batteries have a limited life. So how batteries work, like in your phone, you might notice that after a certain period of time, the kind of efficiency of your battery in storing the charge drops off, and that's similar for electric vehicles. So many charging cycles will eventually reduce the efficiency of your battery. So what they do is, once you hit about 80% efficiency, they feel like the car, it's not the most efficient thing after that. And that's, I think, it's an average lifespan of about 7 years. And that brings down your battery efficiency to about 80%. Now, after that point, there are two things that can happen, or three things that can happen. The one is it can go to landfill, and we're obviously trying to avoid that actively. What a waste. The second thing that can happen is it can go into what we call second life of batteries. So that's where it goes into a storage system. So you can put together a big, almost like an enormous battery pack, and you can take, say, energy from your wind turbines. At the moment, it is absolutely wild in Scotland. We're having huge wind energy being produced. And if you can use that to charge up your slightly less efficient batteries for cars, but perfect for energy storage, you can use it for that. And the third thing you can do is recycle. Now, I don't know if you've ever seen a battery in one of these electric vehicles, but there are absolutely tons of tiny parts to it. So what they do is they can take it out of the car, and that takes approximately 4 hours to take one of these big batteries out of the car. And after that, then to actually strip it down to all the various components, at the moment, it has to be done by humans. We don't have the technology for, the little cool robotics to take it apart. So it's a really time-consuming process. And one of the other big problems is that we stick things in there with super glue to stop any rotation, and super glue is made to last. So those are some of the issues in terms of actually recycling them. But people are doing it, and that technology is absolutely being developed, because there's no way you want to waste all the lithium and the graphite, well, actually graphite's a bad example, cobalt and manganese in the battery. So yes, people are absolutely trying to use that. Just to comment on the wind turbines, they have these very large, very, very powerful neodymium iron boron magnets usually. And so they I think they weigh kind of more, almost 10 kilos. They're very, very heavy. They're incredibly powerful. So actually, you have to be incredibly careful when you're stripping them out, because if you've got two on one side, you don't want to be in the middle of two very, very powerful magnets. So it's quite a technically difficult and kind of dangerous thing to do. But those magnets are definitely being recycled, because the neodymium, which is a rare earth element, is incredibly valuable, and people are definitely reusing and recycling those.
That's a great question and a great answer, Emma. Thank you. Mike up next. So this one's about industrial clusters, and it asks, should we take advantage of industrial clusters by targeting them using industrial ecology so that waste material and heat are redirected for use elsewhere in the cluster locality, thus reducing the carbon footprint?
Yeah, I mean, these are really good questions. So, I mean, for those of you who are not familiar with the clusters, that there are two at least that last week were announced by the government as being funded by the government. So that was in the northwest of England, around Liverpool and Manchester, in the northeast of England. And both of these big industrial clusters are, refineries, to some extent steelworks, fertilizer factories, really, really big users of energy, really big emitters, which are in a group together. And I think the questioner is really quite right in calling it an ecology, because it is an ecology. Kind of a word that ecologists probably wouldn't recognize, but in this context. But basically, they kind of feed off each other, in the sense that to some extent, some of these industries are dependent on each other. But one of the points that I would say is that I would say actually that they're not really thinking enough about some of the extras that they could bring in. So for example, some of the big clusters are thinking about how do we make hydrogen? So they're thinking about maybe you can do it by electrolysis, or maybe we can do it by manufacturing it from natural gas. So when we manufacture it from natural gas, we need to get rid of the CO2. So we bury it offshore in these rocks under the sea. And then we've got our hydrogen, so we can run our hydrogen buses and our trains, and we can maybe even heat houses with hydrogen. So that's all great. But in fact, you know, there's heat produced. So for example, refineries produce heat. And I think that there is an extra that could be done here. So some of the clusters could be thinking about storing excess industrial heat. I mean, it is done, but probably not enough. I think these clusters have enough on their plates thinking and worrying about how they're going to do the big stuff. So you can imagine how much energy a steelworks uses. How do you decarbonize that? Or a cement factory? There are such big questions here. I mean, in a way, it's easy to decarbonize some aspects of our economy. You know, wind and solar are kind of a gift. They're not too difficult to do. But big industrial clusters are hard to decarbonize, and it takes a lot of engineering thought and geological thought. But I agree with the question. I think probably they ought to be thinking a bit more, particularly about heat storage, excess heat storage, because you could do that under the ground. And one of our new test sites that we're also opening, which will be open next year, it's called UK GEOS Cheshire, and it's going to be near Chester. And we're going to be exploring that very question. So can you just store excess heat, say from a power station or a refinery, in the rocks under your feet, in that zone where the rock is, say, 16, 17 degrees C, perhaps at 100 meters depth, so that, you know, it's kept warm. And then in the wintertime, when we need it, we can just pull it out without any kind of, you know, penalty or difficulty. And I think that really needs to be done as well. So our new experimental test site will be precisely looking at that question. Can you actually do it? And is it an efficient way of storing large amounts of heat?
Great, thank you, Mike. Okay, we're back to Alan on this next one. What type of mechanisms would enable excess floodwater to replenish groundwaters? The excess floodwater and the groundwater with capacity may not be in the same place. Also, the floodwater may not have any naturally quick pathways to the groundwater. They're really testing you this evening.
Great question. And yeah, I kind of agree with the tone of the question as well, because this kind of approach is seen as a good kind of technical fix to a problem. Hey, we can do this, but it is really quite complicated and might not always work. So I suppose a mechanism is what normally happens in a river. If you've got a river that's flooding over its banks, it will fill up the floodplain either side and soak into the gravel aquifers there. So that's what these floodplains do. They soak up water not just on them, but underneath them as well. So there are ways really of doing it next to rivers, and particularly in where I generally do most of my work, which is in Africa and in South Asia, that's being thought of quite a lot and being done quite a lot. So when you have rivers that only flow for a few months a year, making sure that water doesn't get wasted by going out to the sea, but is captured next to that river. But there have been other sort of much more engineered approaches, some of them done in the UK, where excess water is treated and then injected actually into the aquifer, so it goes down boreholes and then goes into the aquifer system there. But of course, it's got to be treated and of high quality, because you can't have stuff going in there that's got bacteria in it. But the ones where the areas where they've kind of got floodwater and spread it over a large area, you know, to let it infiltrate into the ground, they need to be cleaned quite often, because the silt settles out and then they stop working so well after a few years. So there's quite a few. There's been trialled in Ethiopia as the waters comes off the Ethiopian highlands onto the plains. Little dams we've built to help groundwater infiltrate there. But yeah, we found that they reduce their productivity after a few years. So you need to be in with bulldozers and make sure that the silt is removed. So it's an ongoing challenge, and a lot of people are working in this area. And I would kind of agree that it's not going to be a panacea as an answer. It's going to have some challenges to be adopted widely.
Thanks very much, Alan. There's actually a question here that I can answer, so I'll give the three of you a quick break. There's a few people asking if this presentation will be available in the coming days. I think a few people may have to leave about 8 o'clock, and I've said how much they're enjoying it. So just to make clear, we will send around a link in the coming days with a video recording of the entire presentation. And any questions we don't have time to answer, we'll do our best in a Word document to answer these and share them with everyone who's registered for this event as well. So the next question is for Emer, and this is one that I've been thinking about myself actually. So how do people decide whether it's better to use electric buses versus hydrogen powered ones? I think probably the same for new kind of eco cars as well. What do we need to consider?
Well, I suspect you'll probably take the first bus that comes, if that's the one you need. But no, I get your question. It's very interesting actually. So at the moment, the technology for electric buses is much more developed. You will see far more electric buses than you will hydrogen buses at the moment. I think it'll come down to how quickly the hydrogen network is developed. As Mike was saying, you know, it involves a massive amount of infrastructure that needs to be put in. And we can see that the electric infrastructure is already kind of going up quite quickly. You'll probably see charging points at, you know, all the services, and you know, probably even your work might be beginning to put them in and things like that. The amount of metal in an electric vehicle is really high. And some of those metals, like I say, lithium, you might have seen a picture in the presentation. Most of the lithium comes from brines. What happens is they pump the brines onto the plane basically, and it evaporates off, and you're left with kind of lithium salts that then get processed. It's quite a water and energy, well, not so energy intensive, but relatively energy intensive process. And then for cobalt, that most of the cobalt in the world comes from the DRC, which has, in certain parts of it, has a history of using child labor to extract metals, not necessarily cobalt, but other things. And so if we think about the kind of impact of the metal use and the metal quantity that are in your electric vehicles versus a hydrogen one, which to my understanding doesn't need quite as many metals. You still need things like platinum and graphite that actually go in the fuel cell, but they're a bit more widely available than things like cobalt. So it's a really difficult question, but I think overall, if hydrogen comes online and we have these networks, particularly for places like the Northwest Highlands of Scotland, so getting kind of those big charging networks in would be quite difficult, but perhaps having tanks of hydrogen that can be refilled, like you see petrol stations being refilled, maybe that's easier. It's a really good question, and I don't know. And I think we kind of consider hydrogen a disruptive technology is what we call it. So there's quite a lot of focus on critical raw materials for batteries and that, but hydrogen is seen as disruptive and might really change the market. A great question. We do think about this quite a lot.
Smashing. Thanks very much, Eamon. So this next question is for Mike, and it asks, are there any disadvantages of storing carbon underground? Particularly, what are the effects of doing this on groundwater?
Yeah, so another good question. So yes, there would be disadvantages if it leaked, if this carbon dioxide was to, once you've put it under the ground, start leaking back up. So we know that that is bad because you can see it in volcanic places in the world. So if you go to parts of Italy, for example, if you've ever flown into Rome Airport, there's some fields next to Rome Airport and you can see they're bare of grass. And that's because there's natural volcanic CO2 leaking up from underneath the ground. And that happens in Italian cities kind of quite a lot. So we know that it's not a good thing to have CO2 leaking from deep under the ground. The second thing is you wouldn't want it to leak into the sea either, because it would make the sea, more acidic. So that would obviously affect, living things. But having said all that, what we know is a couple of things. The first thing is that we know that if you store the CO2 in the right place, if you dispose of it in the right place underground, and we're really talking about very deep, this is more than a kilometer below the surface. We know that in at least 2 or 3 cases, naturally, CO2, which has been created by geological processes, has stayed underground for literally millions of years. We know we can prove that. So we know that there are cases where carbon dioxide manufactured naturally by geological processes simply sat under geological structures, which we normally call traps, and not moved for millions and millions of years. So we know it's possible that CO2 can be naturally kept in a place without moving for a long, long time. But we also know from our own actual storing carbon work. So there's a place almost slap bang in the middle of the North Sea. It's a place called Sleipner. And it's a place where for many, many years, for decades, experimentally, we've been injecting carbon dioxide into rocks about 1 kilometer below the seabed. And they've been doing that from a gas platform. They actually take the CO2 out of the natural gas and put it back in the ground. And that CO2, we can prove, has stayed there and hasn't done anything for all the time that it's been down there. We can prove it because we've monitored it using seismic methods and other methods. And there's no evidence that the carbon dioxide is moving. So really, I would say that it wouldn't be good if carbon dioxide leaked, but it's well within our ability to store it or dispose of it in places where it will not leak.
That's brilliant. Thanks very much, Mike. Okay, so we've got a question back to flood waters now for Alan. And it asks, flood areas that have been put to use for human needs are still prone to flooding. Should any building constructed in areas with high risk of flooding be built on concrete stilts as almost by standard?
Good question, yeah. And yeah, particularly for the UK, where we seem to like building on floodplains. I mean, it's difficult because the clue is in the title, they're floodplains. And you know, there's reasons why these places were not built on for many hundreds of years. And I think sometimes we, with our engineered defences, have thought, okay, they're going to be protected, these areas. And you know, there's been lots of flood modelling done, statistical modelling to see what will be the return period of flooding, how these flood defences that have been built, will they protect against a 1 in 200 year flood? But with climate change and with the increased rainfall events, you know, engineers and hydrologists are rethinking a little bit of how frequent floods might happen or different types of flood events might happen. So building on floodplains is always going to be risky because it is because they are flooding, but they can be protected to a certain degree. So there are already, I mean, a lot of buildings built in floodplains have the lower floors as garages or something else rather than houses. So that there has been a lot of changes, I think, in the way that people do construct properties on floodplains. And if I could add in another bit of the kind of research that we've been doing over the last kind of 10 years is look at another threat. I'm sorry, this is not great news, but something that had been forgotten about a little bit was groundwater flooding. So you might build a nice wall to keep out the river water, but if you've got permeable deposits underneath, what you can find is that water sneaks under them and comes up into people's basements. So quite a bit of the work we've done, and with councils and district councils looking at flooding with them, is I'll have stories of people saying, well, the water came up before it came through the door. So we have to also think about this kind of groundwater flooding, and that might mean altering your flood defences. So we've helped design some where you put in ditches to help lower the water table behind flood defences and such like. So I think there's a lot to be thought about to continue to construct properties on floodplains, both in their design, but also on the types of flooding that occurs within floodplains.
Thanks very much, Alan. Okay, now this is my type of question, and this one's for Emer. If you had the choice to take a bus or a train, which would you take if they both leave at the same time and duration is almost the same? It's like one of those old maths questions, isn't it, really?
That is a really good question. So there's loads and loads of different factors to weigh up. If you take the cost out of it, if you're just going purely on your carbon footprint, generally, I think the answer will be train. But if we kind of dig a bit deeper into that, I think, is it like 2/5 of the UK rail network has been electrified? And if your electric source is renewable or a low carbon option, then you actually have very low carbon emissions, particularly on those lines. Some of them have diesel, but when you consider how many people are being transported by the train, the CO2 footprint per person drops dramatically. Buses can often be more, if they're full, they can have a pretty decent carbon footprint, but it would still be higher than your train. That would be the answer, I think, is the train. I don't know if Mike, do you want to weigh in on that?
No.
No.
Nicely dodged, mate. Thanks, Emer. This next question is for yourself, Mike, and it asks, why doesn't taking up groundwater from heat and water, so I think it means from mines, lead to the same problems as fracking, or potentially from geothermal lead to the same problems as fracking?
Yeah, it's a good question. So fracking is a very different thing. Hydraulic fracturing, if you're not aware of, it's a kind of nickname for hydraulic fracturing. And hydraulic fracturing was kind of invented in America, well, commercialized in America. Basically, it's injecting water in enormously high pressure, like 700 atmospheres, like 800 atmospheres, so that you go down into a rock that contains gas naturally, but the gas is sort of held in these small spaces, these small pore spaces that Alan described. And by doing that, the water cracks the rock and the gas comes out. As long as you suck the water out, the gas comes out after the water. That's hydraulic fracturing, and it's been used a lot in America, in Canada, Mexico, Argentina, China, to get natural gas out of the ground. Now, the kind of geothermal that we're talking about doesn't involve any kind of injection of that type. In fact, what we're really doing is, in the case of coal mine geothermal, the cracks are already there, if you like. The reason why the water flows so well in these old coal mines, the reason why this warm water is so available and accessible is because we've made holes in the ground. I mean, that's what we've done. That's what mining is. And because we've stopped pumping the mines, which of course you had to do during the days of mining, otherwise the mines would be full of water. When you stop pumping them, they fill up with water, and that water warms up. So in effect, what you have is an extremely accessible sort of warm water, and you're not actually stimulating it or doing anything to it in order to make that water flow faster. You've already kind of done it. So it's not like hydraulic fracturing at all. And the same is true of straightforward aquifer geothermal. So warm water geothermal, you should be able to extract the heat without doing anything to it. When you go deeper for geothermal, where the rocks are tighter, so that's a phrase that geologists use, it just means where the pore spaces or the little spaces between the particles are much smaller and gummed up with other minerals. Where it's like that, you would have to do that. So it's called enhanced geothermal. And essentially what you do is you squirt some water in order to loosen up the rock a little bit so you can get the heat out. But that's not what we're talking about here. Deep geothermal of that type is very different. What we're talking about is something which is much more benign. It's really using the natural heat of the earth at quite a shallow level to heat houses, either from coal mines or from natural aquifers. So it's not a problem that we see.
Great, thank you, Mike. Okay, so this next one is back to Alan, and it asks, if companies and people in general know that they can use fresh water from underground, then could this possibly allow companies to not bother to conserve water and just continue to consume water? What is in place to remind society that there's a limit to fresh water if they do not see what they're extracting?
Great question, and one that I ask myself pretty frequently. One of my moral dilemmas is, by telling everybody about all this groundwater, are they going to start using it all and causing lots of trouble? So in the UK and across Europe, we're really good with regulation about water abstraction. So In Scotland, it's SEPA, and England, Environment Agency, will really regulate the amount of groundwater that's abstracted, and they take into consideration how any water abstraction will affect rivers or other users of the water. So it's taken quite a while, but in the UK, I think we've got a really good system now for trying to protect other users of the groundwater, and also the river environment, you know, because groundwater eventually flows to rivers and supports the base flow. So I think we're really well regulated. Where the problems come in are, again, in large parts of Africa and South Asia, where regulation is not so good, and also the US has had big problems. They're only recently getting some of their legislation in order to stop some of this extreme overexploitation. And if you're a user of this groundwater, so if you're drilling, the only way you can tell that the groundwater is going deeper is because your pumping costs get higher, because the water level is going down in your well. So it's economists call this the sort of classic tragedy of the commons, the common pool resource, because you know, basically everybody's accessing this groundwater, and the person with the most money and the biggest pump will win, because they'll be able to draw down the groundwater beneath other people. So it is an issue, and really regulation or some sort of community management. So there's been some good examples, particularly in India, where people get together to manage jointly their groundwater resource, so that the people with shallower wells, who often have less money, are not disadvantaged by the big agricultural producers who pump from a lot deeper. So this is something which I and a lot of groundwater scientists spend a lot of time agonizing and thinking over how to best manage groundwater for the benefit of all users, and particularly the most vulnerable users, and also for the environment.
That's another great question, and I'd like to follow up on that, if I may, Alan. I mean, you talked about an incredible stat about a Californian aquifer. I think over 100 years, the ground had subsided by about 7 meters due to depletion. How is that tracked or studied or monitored? Like, how do we get that figure over such a long time frame?
So the Californian Central Valley Aquifer, I mean, some of you might have been to California and seen the amazing kind of agricultural productivity there. They've been pumping groundwater for about 100 years, and that's helped to irrigate, you know, all these big the pistachio nuts and all the other things that are growing there that we love. But what's happened is, by pumping that out, the water level's fallen, and because it's all kind of soft deposits, it's gravels and sands, is that they compress more. So once the water's out of them, they compress more, and it's gone down. So nowadays, do it by satellites. So it's satellite INSAR, they call it. So they look at how the satellite how they beam down some waves and measure the interference between the waves as they're coming back up, to measure really precisely the elevation of the land. But originally it was done the old-fashioned way with surveying with spirit levels and your telescope thing. So guys would have surveyed in from the mountains at the side and seen how the ground level had fallen. And because it was all kind of soft, it didn't get really cracked as it went down. You know, it kind of all kind of scooshed down together, if that's the right word. So in the past, guys with hats and beards and spirit levels and telescopes, and nowadays with satellites.
Great stuff. Thank you very much. Okay, so this is a question for Emer now. I think the question is asking, we can now create artificial meat. Where are we in creating, well, it says here artificial metals, but I think it probably means alternatives or synthesized alternatives that we could use in place of metals. Is that an area of research that's happening at the moment?
So yes, we can't create metals. They exist. They're elements. We can't create them. However, we do create kind of, like I said, alloys. So we mix metals together that perhaps will have each will have a specific property that when we combine it makes exactly the right metal we want for the product or for whatever our manufacturing needs are. In terms of alternatives, do you mean maybe like substitution? that's a big area of research. So if we take the example of some of the rare earth elements that I was saying are in magnets. So you can add a little bit of dysprosium into your magnet, and it increases the kind of some of the very important properties of the magnet. However, it's very expensive. So a lot of companies will try and kind of design out that element. But then what happens is you don't get quite exactly the same magnet. The price of the metal will drop, and then everyone's like, oh, it's really cheap. Let's add it back into our magnet. So there is, although people are trying to kind of work on substitution and kind of changing the chemistry of the magnets or the composition of different things, often it comes down to kind of the market and the price of your metal, and that will impact it. But there are certain other metals then that are quite rare, so or that are kind of hard to mine, kind of the tellurides and things that we use maybe in photovoltaics. And I know there's a lot of research going into substituting those out, just because they're often a byproduct of mining a bigger commodity or something, and they aren't always processed. They often maybe go to the waste. So yes, it's definitely active research and substitution for different methods.
Brilliant, thank you, Emer. I'm just looking at the time. I think we've got time for another handful of questions, but we're definitely not going to get through everything that people have asked, and there's still lots of cracking questions. So just a reminder, we will try our best to answer them offline and share a document in the coming days after this presentation is finished. Okay, so in the last kind of roundup of questions, we have one from Mike here, and that asks, what part does nuclear power have to play in the route to net zero?
Okay, so I'm just going to show you a website. It's a National Grid Live update. So you probably can't see that on my phone, but I'm a bit addicted to this website. So if you're really interested in where our energy is coming from right now, right this minute, you can log on to the National Grid Live Status website, and you can see where our power is coming from right now. So in fact, I'm reading it. It's about 12 gigawatts is coming from combined cycle gas, so fossil fuel. That's 35% of our energy. Something like 11 gigawatts is coming from wind, so 33% of our power is coming from wind. 0.82 gigawatts, so 2% is coming from hydro. And about 5 gigawatts, 5.07 gigawatts, 14% is coming from nuclear. So that is something that you will probably see day in, day out. What you'll notice if you follow this website like I do is it really changes a lot. Coal is zero at the moment. Actually, coal is zero, but sometimes coal goes up. Sometimes gas combined cycle goes up, but nuclear tends to stay about the same because it's base load. It's really good. Nuclear is really good at producing lots of electricity in a reliable way, day in, day out. It's not intermittent because we basically control it. So it's really valuable. But when the question really depends on where you live. So in the UK, we do like our nuclear, and we do have, as I say, around sort of 15%, 5 gigawatts, so 5 billion watts or 5 billion joules per second coming from nuclear. But in France is even more. I mean, they really like nuclear in France, but in other countries, like in Germany, they've kind of fallen out of love with nuclear. And in Japan, they're kind of at this moment falling out of love with nuclear for various reasons that many of you probably realize, Fukushima, for example. So it kind of depends where you live. And broadly speaking, people tend not to like it. When you explain about it, people tend not to like nuclear, even though it has a generally very good record of safety. I guess what spooks people about it isn't the safety of its record or the fact that it produces all this power in this very reliable way. It's the fact that it produces waste. So in the UK, we've got something like 50 years of civil nuclear waste, 50 years worth of waste that we have at the surface at the moment, and it's kept in tanks. And it's got to be got rid of, and it's going to have to be got rid of underground, almost certainly in a deep place where it'll never be got at again. So this is what kind of spooks people about nuclear. So on the one hand, it is low carbon, it is very reliable, it's very powerful, but it's also it does produce this waste. So, you know, depending on who you talk to, you know, people have different views.
Thank you very much, Mike. So, okay, on to one of the last kind of questions, and this one's for Alan. Your groundwater productivity map of Africa showed high productivity in desert areas. What is the prospect for using groundwater to green the deserts to capture CO2 and provide biomass/food?
Excellent question. And it was one of the interesting, surprising things when we developed this groundwater map for Africa, to really see that so much groundwater resources is under the Sahara Desert. So these old sandstone aquifers, hundreds of meters thick, with water, groundwater, that was in place there thousands of years ago. So when it was actually wetter in the Sahara Desert, these aquifers filled up. So some of the water there is up to 1 million years old. So it's really old water. So we kind of think of it almost as fossil water. So that kind of groundwater, think of it in the UK and other parts of Africa where a lot of people live, it tends to be replenished quite frequently, you know, once or twice a decade, sometimes even every year. So the kind of water table doesn't keep going down and down. But these aquifers underneath the Sahara are truly kind of fossil groundwater. So if you use it, it doesn't get replaced, certainly in our lifetime or our generations to come lifetime. So how that water is used is really important. It's a kind of societal discussion, really. How do we use this resource now, because we're going to use it up? So, you know, for example, in Libya, they developed this fossil groundwater to pump it up to Tripoli and to the coast to help the kind of cities survive, and they were kind of mining that water, but not at a huge rate. There's also water mined in Saudi Arabia to grow wheat. Now, some of us might think that's not a great economic return for all that effort and energy to pump it up just to grow wheat, which could be grown very easily in Canada or the steppes. So to use up that groundwater, I think got to think what could we use it for? If there was an amazing way that it could do something massively useful to help with climate change, then that might be a decision to decide to say, yeah, let's use it for that. If it's just to help us out of a wee bit of a jam in the short term, it might be too expensive, both in terms of money and carbon, and future, you know, for future generations for us to use up that groundwater. But it's a really good question. And when I first published these maps, which was about 7 or 8 years ago, you know, I was asked that a lot. I had to write various articles, different newspapers, about how we use this huge water under the Sahara. So it is you feel because it's there, we should use it for something, but it might be better to leave it in the ground.
Brilliant, thank you, Alan. Okay, second to last question, and this one's for Emer. If hydrogen-powered engines produce their own electricity, is it best to have large vehicles powered by hydrogen because they start instantly and don't have to be recharged, using less materials for them to run? Isn't a hydrogen-powered vehicle a stripped-down battery anyway, without having to carry bulky electrical storage, in a sense?
Yes, is the answer. Yeah, absolutely. It is essentially stripped back. You know, you don't have the weight of the battery. I think a Tesla weighs a ton or something there in very, very heavy vehicles. But for the large goods vehicles, I know that Australia has just commissioned its first hydrogen-fueled coach, like a big bus for kind of long-haul travel. There's definitely people looking at hydrogen-powered ferries and kind of the container ships, those kind of things that can store the hydrogen on the ship, can you know, refuel themselves and are able to then, you know, power along without having enormous amounts of kind of diesel pollution. There's also quite a lot of work going on in developing heavy goods vehicles, developing hydrogen for heavy goods vehicles. And yes, electric vehicle technology, those batteries, I don't think they'll ever be used for heavy goods vehicles, because the amount of energy it would take to charge up and the size of the battery, which would be incredibly heavy, it's just not really practical. So yes, I think hydrogen will be the way that goes.
Thanks, Emer. For a minute there, I thought your answer was just going to be yes. And I didn't have the next question ready.
You're okay.
Okay, so we're on to the last question. So just again, there's still lots of great questions we've just not had time to get to in the live chat, but we will, like I say, answer them after, and we'll send around the link. So this question is open to all panelists. And if we could start with probably Mike through Alan and finish with Emer. And it simply asks, what is the most surprising geological finding that you've discovered so far during your research?
I can't remember very far back, so I'll just have to tell you something more recent. So the most recent, I've been working in Israel, and I'm working on the Dead Sea Fault, which is this fantastic fault that runs up the Dead Sea and makes the Dead Sea so low down, and also caused destruction in the past. So the falling walls of Jericho were probably destroyed by the Dead Sea Fault. And until recently, it was thought to be about 35 million years old. So people thought that it had only appeared about 35 million years ago. But the work that I did with somebody else from the Geological Survey of Israel suggests it could be 250 million years old. So there's a good one for you. Follow that.
That's pretty good. I think one thing about working here is that you're surprised very frequently, aren't you, by looking at nature and seeing what's there. I suppose one of my most recent surprising findings was when I was looking at groundwater depletion in northern India and Pakistan. So groundwater levels have been really depleting there over the last kind of 10, 20 years. So we put together lots of data for the last 100 years. We managed to find records and put it together. And what we found, that when you looked over 100 years, groundwater had actually accumulated by at least 5 times more than it had recently depleted in the last 20 years. So groundwater levels had been going up and up and up and up the last 100 years. And the reason for that was the big irrigation schemes there, the river irrigation schemes with the Indus and the Ganges, had been leaking water into the groundwater. So the aquifers were filling up and up and up and up and up. So that was a really surprising one, because we were looking for water levels going down, and we found that water levels had been going up.
Cool, that's really cool. Mine is a bit of a throwback to when I was a geology student. So I come from the west of Ireland, and we have a lot of limestone. So I knew all about carbonates and limestones and fossils. And when I came to university to study geology, I found out about a rock called carbonatite. And this is actually a volcanic rock that is entirely made of calcite. So the same mineral that makes up your limestone can actually be derived from volcanic activity, which is literally the coolest thing I think I've ever heard. And carbonatites are my favorite rock. There you go.
Only geologists have favorite rocks.
No, everyone has a favorite rock.
Thanks everybody for a really wonderful talk. So thanks very much to Emer, to Alan for really great explanations and also really interesting answers to questions. And thanks to JP, who's helped us all the way through, filtering our questions so we only got easy ones, and making sure that we kept to time. So thanks very much, JP, you did a fantastic job. I hope this little talk will help you think a bit differently about your house, where you live and your ordinary life, when you go to school or when you go to work, or the way that you use transport, the way you use energy, and maybe think about the way you use water as well, and the metals that are in the household items or the machines that you use every day. So I hope that's really been something useful for you. And if you really want to learn more, then we can answer questions, following the meeting later on. And we can also you can also check the BGS website, because there's lots and lots of information on the British Geological Survey website, which is www.bgs. What? I've forgotten.
I think it's ac.uk.
.ac.uk, yeah, I should know after 22 years, but we'll go on and have a look. So thank you very much, everyone, and have a lovely evening. Enjoy the rest of your evening. Bye.